Hi, so this is a joint work with Mahsa, MohammadTaghi, my advisor, and Alex. So assume that you want to protect a set of valuable targets from a possible attack, and you have a set of patch holes that you can use to protect these targets. And the problem is that these targets could move over time, and therefore you also have to move your patch holes. So the problem has a wide variety of applications and has been deployed in many places. So for example, protecting aid convoys with overhead UAVs, or protecting vessels from pirate activities, wildlife protection, protecting Staten Island ferries of New York, or protecting urban transit systems, and many other deployments. And let me give you a formal definition of the problem. So we consider from a game theory perspective, we assume that it's a zero-sum two-player security game. There's an attacker and a defender, and both time and space is discretized for the moment. I will not go over the continuous case in this talk, but we also consider the case where the space is continuous. Okay, so there are 8 moving weighted targets. So in this figure, the y-axis denotes the space and the x-axis denotes time. So, and these red points denote targets. Each of them have weights and they move over time. The targets are not required to be in the discretized positions, but the patch holes are. The patch holes, so the defender has k homogeneous patch holes, or resources, and in this example the resources are denoted by these thick black lines, and this is how, for example, one resource moves over time, and these are, as I said, the targets, and again, the resources could only land on the discretized positions. The patch holes also have a maximum speed delta. So if a patch hole is at location m1 at time t and at location m2 at time t plus 1, then the difference between m1 and m2 should be at most delta. Also, the patch holes have a protection range. So we say if the target is within the protection range of at least one patch hole, it's protected. The protection range of the patch holes is denoted by these gray areas around the patch hole paths. So for example, this target at this time is not protected by any patch hole. So the attacker's strategy is to choose one target and one time point and attack that target at that time point. And the defender's strategy, I'm talking about the pure strategies here, and the defender strategy is a value trajectory for each patch hole. The attacker gets the weight of the target that he attacks if that target is not protected by any patch hole. And again, it's a zero-sum game, so basically the payoff of the defender is the negative of the payoff of the attacker. And our goal is to give a best strategy, meaning basically min-max strategy for the defender, and we want it to be polynomial in the input size. And note that even m, which is the number of spatial locations in a specific time point, is exponential in the input size. That's just a number that's given in the input size. So we don't want it to be polynomial even in m. And the main difficulty is that the number of pure strategies of the defender is huge compared to the input size. So you can choose any subset of k of the locations as where you put your patch holes in a specific time point, and if the speed limit is, for example, very large, this could be as large as n choose k to the power of t. So this problem has been considered by multiple papers. In 2013, Fang et al. Introduced the problem, and they gave a polynomial time algorithm for the case where the number of patch holes is constant. in 2014, Su et al. Gave a framework that under different assumptions gives polynomial time algorithms for the problem, for example, when the number of time layers is constant, or when the protection range of the battlefields do not overlap, or when the targets are homogeneous, in that they do not have weights. And interestingly, in EC last year, it was shown by Su that the general case with another condition on the acceleration of the path rolls becomes NP-hard. So we answered the general case without acceleration in this paper, and we show that it's indeed a polynomial time. There exists a polynomial time algorithm to solve it. So our algorithm consists of three main steps. The first step is partitioning the spatial position so that we kind of get rid of this dependence on M, which is not a polynomial in the input size, as I mentioned. I'm not going over the technical details of this part, but just to give you an idea of what we do, for any time point, we partition the space into intervals such that any 2 points in these intervals are equivalent to each other as far as the problem is concerned. Okay. The second step of the algorithm, so for now, assume that M is small, and we are trying to give an algorithm for the problem when M is small. So the second step, assume that we know at what time the attacker is going to attack. So assume that we know that the attacker attacks at time t, and we want to give an algorithm that give a min-max algorithm for the defender knowing this data. So what we do is to use min-cost fellow in an LP. So consider this graph. So we have a source, a sink, and a grid of k times m vertices. Remember that k is the number of resources and m is the number of spatial positions. And the graph is as follows. So the source has directed edges to all the vertices in the first column, and the sink has incoming edges from all the vertices in the last column, and each vertex has a directed edge to all the vertices in the next column that are above it. Okay, now every path from S to S prime denotes an assignment of path rows to positions. Consider this path for example. The first column specifies the location of the first path row. So this means that the first path row is at location 1, and the second path row is at location 2, and the third and fourth path rows are at location 5 both. So it could be shown that there's a one-to-one mapping between assignment of path rows to positions and these paths. Similarly, for a randomized assignment of path rows called a mixed snapshot, it could be shown that a fellow of unit 1 from S to S prime could basically describe a randomized assignment of these path rows to these locations. So basically what we do is that using the typical linear programming representation of mean cost flow, by defining a cost for each a cost vector for each edge, we basically find the mean cost flow and solve the DLP to get the best strategy focusing on one specific time point. Now the problem is how to combine all these time points to give an algorithm for the general case. Well, it's easy to imagine that we can probably combine all these LPs in one LP and minimize the cost over all the possible time points. But the problem really is that these flows should be compatible, and they may not be compatible because of the speed limit that we have on the path row. So for example, if we have an assignment for time 1, it has to be compatible with the assignment that we give for time point 2. So for this, as I said, we combine all those LPs in one LP and add this compatibility constraints and show that this is actually a good constraint. So let me give you some intuitions about this compatibility constraint first. So, for any range A at time t, the expected number of resources in A should not be more than the expected number of resources in the feasibility region of A in the next time layer. So, what it means is that this feasibility region specifies all the positions that are accessible from A, right? So if a target is at A at time t, then it definitely will be in the feasibility region of A at the next time. So the expected number of resources in A should not be more than the expected number of resources, the number of patches in the feasibility region of A. So this is easy, it's easy to show that this is a necessary condition. But the problem is it really sufficient? Having this constraints, could we be sure that the solution of the LP is actually optimal? And there exists a strategy satisfying this LP or not? And the answer is somewhat yes. So the technique that we use is that after the LP finds the solution, we adjust the solution of the LP and find another solution. And we ensure that there is no crossing edges in the flow. So if there's, for example, a crossing edge, if two crossing edges both have a positive flow, we change the flow such that this becomes, such that we get rid of this cross in the flow. So crossing at vertices is okay, but the edges should not cross each other. So after we post-process the LP and make sure that this condition is satisfied, we show that this will still be a valid solution of the LP. But the problem was that we couldn't, by linear constraints, ensure this in the LP, so we had to post-process the LP to get this. And after after we're sure that there are no crossing edges, we will construct a strategy based on the flows. So the main problem of crossing edges is that, so consider this flow. So here there's a crossing edge. So the topmost path is not defined here. So for example, this path until this column, this path until this column is the topmost one, but after this crossing edge, it becomes the second topmost one. And this topmost path is what is basically the path that we use in constructing the strategies. But once we are sure that the edges do not cross each other, the topmost path becomes well-defined. So what we do after that is to show that the topmost path of time t is always compatible with the topmost path of time t plus 1 using that compatibility constraint that we have. So this enables us to first get the topmost path of all of these flows. We know they are all compatible with each other, construct a pure strategy based on these flows, and put it in the support of the final mixed strategy that we report. And then remove them from the flow, and we recursively do this. And that's it basically. So the open problem, there are like a lot of open problems to be answered in this problem. So for example, we assume that the targets only move along a one-dimensional space. What about like a 2D space? Or my guess is that the 2D space should be harder, like computationally harder, but even an approximation solution would be very nice. And another technical assumption that we had is that in the input, the location of all the targets is given. This is a somewhat unrealistic assumption because if you know how the targets move, the scheduling doesn't really mean anything. So maybe the online version of the problem or something like that would make more sense. And Yeah, I think that there are a lot of different cluster extensions that are all interesting. And since this problem has many real-world applications and deployments, I think that would be useful to anyone.